All right, in this first example, we're going to find the volume of the solid generated by revolving the region bounded by the curves y equals x squared plus 4 and y equals negative 1/2 x plus 5 around the x-axis. First thing we're going to do, again, is just sketch ourselves a quick little graph of this situation. So we've got y equals x squared plus 4 right there, and y equals negative 1/2 x plus 5 right there. And so the region that these curves are bounded by, or the region bounded by these curves, pardon me, is this region right here. And we're going to revolve this around the x-axis. Okay, so we want, since we're going around the x-axis, we want our radii to be perpendicular to the axis around which we're revolving, the x-axis. And so if we look at this region, the curve y equals negative 1/2 x plus 5 forms the outer boundary of the solid. And so we want the distance from that boundary to the axis of rotation. And the curve y equals x squared plus 4 forms the inner boundary of any particular slice. And so we want that to serve as the inner radius as we revolve the solid around. And so if you imagine what we're looking at here, we've got a washer-shaped solid where the inner radius is going to be the distance from the axis up to the curve y equals x squared plus 4. So that distance right there is going to be x squared plus 4. And the distance from the center to the outer boundary is going to be negative 1/2 x plus 5. And so what we really have going on here is we're finding the volume of the big solid, the solid formed by the outer boundary of the region. So that would be pi times the integral from somewhere to somewhere, we don't know yet, of the outer boundary squared. And we're taking away this smaller cylinder in the middle, and the volume of that is pi times the integral from somewhere to somewhere of the inner boundary squared. Now we can do a little factoring and turn this into one integral where it's just the integral of the outer boundary squared minus the inner boundary squared. And now we need the limits of integration. And I can either set these two equal to one another and solve algebraically, or I can turn to my graphing calculator to find these intersection points. So I'm going to go in here and make sure I'm in the right mode. And I'll graph these two curves, y equals x squared plus 4, and y equals negative 1/2 x plus 5. And I'll go ahead and graph those in the standard graphing window. And now since we're revolving around the x-axis and our integrand is in terms of x, we want the x coordinates of these intersection points. I'm going to go ahead and find those intersection points. 1, 2, yes. I'm just going to move my cursor outside that intersection point so it grabs that intersection point for me. And so I want the x-coordinate of this intersection point as my lower limit of integration. That's negative 1.280776. So negative 1.280776. And I want the other intersection point as my other boundary. So I'll run that command again and find where these two intersect. And again, when it asks me to guess, I'm going to move my cursor out past that intersection point so that it gives me that intersection point, and I get 0.7807761. 780.77641. And I'm going to use those limits of integration. And now that I have my whole integral set up, I can go ahead and use my numerical integral to find the volume of this solid. I've got pi times the numerical integral of the quantity -1/2 x plus 5, quantity squared, minus quantity x squared plus 4, quantity squared, with respect to x, from lower limit, -1.280776, to upper limit, 0.7807761, and we end up with a volume of 43.123 for the solid. And that's the end of example 1.